So up to this point, from this derivation of the pressure, we've been able to now get some information about what's happening on the microscopic level from some macroscopic characteristics, things that we can easily measure, temperature and mass. Right, molar mass we know for particles, temperature is something we can measure, and we can then infer roughly how fast, on average, particles are going. But one other thing that's interesting to know is the distribution of those speeds, right? We know the average, but what's the distribution? And so the way we often think about this or plot it is, we have, say, on our y-axis here is a fraction or a population. And then the x-axis would be, we'll talk about velocities and speeds. We'll start with the velocity distribution, right? So this would be for a particular dimension. Say this is, along the x-axis. And so the question is, what does this distribution look like, right? Is everything closely clustered around the average speed, or are things more spread out and you have some particles that are really slow and some that are really fast? What fraction is in a particular, speed range? Right, if we set a speed limit of 500 meters per second, how many of our particles are speeding and going over that? These are the sorts of questions you can answer if you know the velocity distribution. Now, the derivation of this is a bit more involved, and it's gone over in your textbook, in the Macquarie-Simon textbook pretty well, in section 27-2, if you want to go over that derivation. We're mostly just going to focus on the results of that, though. What does this equation distribution look like? And what does it mean for measurements we may make that involve this? So this distribution, this velocity distribution, and the speed distribution, which we'll talk about next, are known as the Maxwell-Boltzmann distribution, named after a couple of famous physicists who worked on this. And the velocity distribution for a particular direction, so we're going to, again, pick x, but this is the same for y and z, as our distribution is f, it's a function of the velocity, and we have a normalization constant, m over 2 pi rt. This is raised to the 1/2 power, so square root. This is just a normalization constant, and then we have the exponential of negative capital M ux squared divided by rt. Oh, there's a 2 in there, divided by 2rt. Okay, so we have an exponential here and a normalization constant. Now the normalization constant, which is out front here, this is just to ensure that if we integrate f of u of x over all possible speeds, or velocities, let me be careful here. In this case, we could have velocities ranging from negative infinity to positive infinity, that this is equal to 1. Because this is a probability distribution, all of the particles have to be represented at any possible speed, right? So this constant out front ensures that this condition is true, right? And so the part that really matters and tells you what the shape of the distribution looks like is this part here, this exponential term here. And if we sort of ignore the constants and just look at what sort of function this is, e to the minus x squared with some constants in there as well, for a given system we're looking at, it'll have a fixed mass, and r is obviously constant, and the temperature should be constant. The basic behavior is e to the minus x squared. And this is what's known as a Gaussian function, or a normal distribution, if you are familiar with that terminology. And what does this look like? So if we plot a Gaussian function, the basic shape of it, and probably you've seen this at some point in your chemistry career, basically it looks like this, except for actually even. This is the hard part about drawing. Okay, that's supposed to be symmetrical. And since we don't have any sort of offset here, the distribution's maximum is at 0, and so it's equal on the positive and negative sides here. And so this is what our f of u of x, and as a function of the velocity, looks like. So we have some particles on the negative side, some on the positive side. So first question is, what does that mean? What does it mean to have a negative and a positive distribution, or negative positive velocity? The other question to think about is, why is the maximum at 0? As we're thinking about this velocity, why would we expect the maximum to be at 0? Or what does that tell us that the maximum is at 0? And then the other question is, now not ignoring the constants anymore, how do mass and temperature affect the distribution? Right, so the general shape is like this, but the distribution can become much wider or much narrower, and that's going to depend on the mass and the temperature. And so we'll look at some of those in upcoming videos.